With Module 8, we're going to begin consideration of the properties and compounds formed by metals, and we're going to focus in this first video on transition metals. Our learning goals for this will be how to infer trends and properties of these metals from the periodic table, and some of the features of their compounds between transition metals and including transition metals. So let's consider where they are in the periodic table. Now, what I'm showing you here are where all the nonmetals are, and you can see that with the exception of hydrogen, they're all in the upper right-hand corner of the periodic table, and they represent about 15% of all of the elements known to us at this point. Now, we've already talked some about alkali metals, lithium, sodium, potassium in particular, but that whole first column of the periodic table are the alkali metals, and they're very active metals. Next to them are the alkaline earth metals, starting with beryllium, magnesium, calcium, and we've talked about them a little bit also, but really only in the context of ionic compounds. Next comes a very central group. These are the transition metals, the subject of this particular video, and they represent 10 columns that bridge the gap between the first 2 columns and the last 6 columns. Next to them, first we go down to consider the rare earth metals. These are actually, they should be inserted at that gap in the transition metals, the 57 to 71 and 89 to 103 gaps. These are actually another group of metals. They're called rare earth metals, although they're not particularly rare. They're called rare because they're difficult to separate from their ores. Finally, there are the main group metals, which are things like aluminum, gallium, indium, tin, lead, and so forth. And then in between them and our nonmetals are the semi-metals, which include elements like silicon, germanium, arsenic, antimony, tellurium, and so forth. Now, the metals themselves constitute almost 80% of all of the elements that we know. So in other words, the vast majority of the elements we know are all metals. So what we want to do is consider what are some of their properties, what distinguishes them from the nonmetals, which we've focused so much of our attention on up to this point in the semester. Right? What are some metallic trends? Well, metallic character is really the ease of removing an electron. All of these are elements for which it's relatively easy to remove an electron, so they have a fairly low ionization energy compared to the nonmetals. In fact, that ionization energy trend increases as you move up in the periodic table and as you move to the right. So the very lowest ionization energies are in the lower left corner of the periodic table. And so all of the places where the metals are represent relatively accessible ionization energies. Should note that metallic character is really a measure of its reactivity. So the stronger the metallic character, the more reactive the metal is. And that reactivity goes in the opposite direction of the ionization energy. In other words, the less the ionization energy is, the more reactive the metal will be. So we see this trend of going to the left and down increases the reactivity of metals. All right, so now let's learn a little bit about transition metals. Here is the group of transition metals that are right in the middle of the periodic table, and the first row of them, which I've detailed on the right, are really the ones that are most common to us. These are also primarily the ones you will find in living things. There are a couple of other metals that do get into compounds that we find in living cells, but most of the ones that we use in regular use in proteins and so forth are in that first row of the periodic table, the first row of the transition metals. The last row of the transition metals are all radioactive elements, and in fact they don't live for very long and are only known for a brief instance of time when they're produced in the lab. These transition metals bridge the gap between the active metals that are the first 2 columns in the periodic table and the last 6 columns, which are the main groups, and they're the thing that allow an expanded valence shell for those lower elements of the main group because they give access to d orbitals, another kind of orbital. So let's take a look at those electron orbital types and see if we can understand how they help us understand the structure of the periodic table. So each orbital can hold 2 electrons. So we're already familiar with s orbitals. They can hold 2 electrons. And in fact, they're responsible, it's when they are I'll say the valence electron orbitals, they are responsible for those active metals on the left side of the periodic table. The first 2 columns are when elements are filling in those s orbitals. The p orbitals we're also familiar with. There are 3 of them because there are 3 dimensions. So there's an x, a y, and a z p orbital. So that means the total capacity of the p orbitals is 6, and they account for the 6 columns over on the right-hand side of the periodic table. This is where we find things like main group metals, semi-metals, the non-metals, and the noble gases are all in this particular part of the periodic table. In between them, we find the d orbitals. This is where they're being filled. There are 5 d orbitals. They have a total capacity then of 10 electrons, and that accounts for the 10 columns that we find in the group of transition metals. Now you notice the d orbitals have some exotic shapes. We haven't talked much about them. I'm not going to ask you to worry very much about these shapes. Just know that there are different kinds of orbitals that can be filled around an atom, and d are the ones that come after p. So these are the ones that are being filled as we go across the elements that are in the transition metal part. So what are some of the properties of transition metals? Well, first of all, they're less reactive than the active metals in groups 1 and 2, that is, the alkali metals and the alkaline earth metals. Most of these metals do exist in nature as compounds, though, so they do react. All of them form +2 ions. Now, this really comes from the loss of their 2 s electrons. It's not from the loss of d electrons from their a menagerie of different orbitals. They mostly form multiple stable ions. You'll need to consult lesson 8a to see the full list of these. But they also often have bright colors, and they exhibit magnetic properties. All right, so these are all very interesting properties that we don't find in carbon framework molecules so much. All right, these last 2 properties, the bright colors and the magnetic properties, are really due to the d electrons in these metals. So this is a new thing that we can experience because we have access now to these d orbitals. So what kinds of compounds can these elements make? Well, we're familiar with alloys already, familiar with ionic compounds, and then there's a new kind of compound that we'll be highlighting in this module called coordination compounds. I'll remind you that alloys are simply combinations of metals, or sometimes non-metals, that are put together in imprecise proportions. So, for example, brass or steel, these represent alloys where we've got mixtures of elements, but there is no definitive proportion of these things that give them that identity. Ionic compounds, on the other hand, are typically composed of a metal positive ion and a non-metal negative ion. These proportions are fixed, so that's why we have empirical formulas for them. And the polyatomic negative ions are incorporated as whole units in them. So some examples of these kinds of compounds include sodium oxide, calcium fluoride, and aluminum nitrate. And the nitrate is an example of a polyatomic negative ion that is incorporated as a whole unit in this ionic compound. Finally, the coordination compounds, and we're going to be learning a lot more about this in the lessons to come, consist of a metal ion, a set of non-metal ions or compounds that attach to that metal ion, and then counter ions on top of that. So they're sort of a curious mixture of both covalent and ionic bonding. They're very fascinating creatures, and we'll learn a lot more about them in the lessons to come.